Hi guys, welcome back to my YouTube channel IBwontcrushyou, and today we are dealing with nonlinear modeling, and this topic is dedicated only for HL higher level. And let's get started. Problem 1. A bacteria culture grows according to the model n equals n0 times 3 to the power of 0.5 t, where t is time in hours and 0 is the initial number of bacteria. Given that initially n0 equals 500, find the number of bacteria after 5 hours. So as you can see, we have to just substitute 4 into t because 4 hours, so t is 4, and n0 we're given n0, so all we need to do is substitute these values. So in 4 equals 500 times 3 to the power of 0.5 times 4, and this is 500 times 3 to the power of 2, so this is 4500. B. Use your GDC to plot n for t from 0 to 10. So we have to type our function with this initial 500 into our GDC and then redraw it on the paper. And this is our graph. It looks like this more or less. And you have to remember about the domain, so we're drawing this graph only from t0 to t10. And in C, we have to estimate from the graph when the culture reaches 10,000 bacteria. So it's hard to estimate from the graph, so we can find it from our graph in our GDC. So we have to just choose gsolve, then x calculate, then enter y value, and our y value is 10,000 bacteria. So t is 5.45, and we can also solve it in solver. So 10,000 bacteria equals 500 times 3 to the power of 0.5 times t, and we can solve it also in solver, and the answer will be the same. Problem 2. The cooling temperature T of a object over time t in minutes follows. T equals 25 plus 18 natural logarithm, and in bracket 10 minus t. A. Determine the domain of T, so of the temperature. In order to determine the domain, we have to find if our function has any constraints. And we remember that logarithms, the number that is in the bracket in logarithm has to be greater than 0. So our 10 minus t has to be greater than 0. So 10 is greater than t, so our domain is for t from minus infinity to 10. B. Use the GDC to plot t for void t. So we have to type our function into our GDC and then, as always, redraw it on the paper. And our graph looks like this. C. Find T2 and interpret its meaning in the context of cooling. So firstly we have to just substitute 2 into T. So we have 25 plus 80 ln 10 minus 2, and now we have to calculate it. So this is 195 Celsius degrees, and we have to interpret its meaning. So basically this is the temperature that this hot object has over 2 minutes. D. Estimate from the graph when the temperature drops below 40 Celsius degrees. So we have to substitute 40 into T as a temperature. So it is 40 equals 25 plus 80, natural logarithm 10 minus t, and we're looking for t, or we can just on our graph find it. So desolve, excalculate, and then we have to enter y value, so 40, and our answer is t 8.79. So after 8.79, and here we have minutes, so minutes. Problem 3. A tank is being filled with water at the rate modeled by V equals 200, and in bracket 1 minus e to the power of minus 0.3 t, where V is volume in liters after t minutes. A. What volume is in the tank initially? So initially you have to be familiar with when we have initially, so it means when time is 0. So we have to just substitute 0 into t. So V 0 equals 200, 1 minus e to the power of minus 0.3 times 0, and everything to the power of 0 is just 1, and in bracket we have 1 minus 1, so 200 times 0, so 0. Of course you can calculate it on your calculator if you are not sure. And in B we have to calculate the volume after 5 minutes, so we have to substitute 5 into T. So the answer is 155.41 liters. C. Using your GDC, find how long it takes to fill 90% of the tank's capacity. So firstly we have to know and of course we have to find what is the maximum capacity of this tank. And in order to do this, we can substitute a very big number into t. For example, 1 million. So we can write it like this, that v and here infinity, because we're substituting very big number. So it will be 200, 1 minus e to the power of minus 0.3 times infinity, and as you can observe from your GDC, this is 200. So 200 is our maximum capacity. And now, because we have to find how long it takes to fill 90% of the tank's capacity, so we have to multiply 200 with 0.5, because 90% is it is the same as 0.9, and this is 180, and now we can substitute 180 as v, and then we have 201 minus e to the power of minus 0.3 times t, and now we can find it in the solver. So our t equals 7.68 minutes, and in D we have to interpret the long-term behavior of v, and as we know from the previous point, from point C, when we have a t, a very huge number, so we can say infinity, our tank reaches its maximum capacity. Problem 4. Given the data points, and we are given 5 data points, you are to test two models, exponential and power. A. Use your GDC to perform non-linear regression for both models. So all we need to do is to type these points into statistics, into two columns, list 1 and list 2, or to spreadsheet, depends on the GDC that you have. Firstly we have to type them, and then just choose exponential function and then power function, and we will get these functions. So these are our functions. The first one is exponential, the second one is power. B. Write down the parameters a, b, and c, d from your regression. So basically we already have these points from a previous point. So a is 1.79, b is 0.571, c is 2.63, and the d is 1.39. And in C we have to plot both models on the same graph. So these are our functions after graphing them. This one is exponential, and this one is power. Problem 5. A population P is observed to grow according to one of two models. And we are given two models, and then given measurements at t1, 2, 3, 4 days. P equals 5, 9.3, 14.1, 18.2. A. Use your GDC to feed both models to the data. So all we need to do is just to type these values, firstly t as x and then p as y, to statistics, to list 1 and list 2, or spreadsheet, depends on the GDC that you have. And then we have to choose calculate regression, and then firstly exponential model. So our equation is y equals 3.57 e to the power of 0.429 times t, and then you just need to exit and choose then logarithmic function. So we have 9.355 times natural logarithm, then t, and plus 4.22, and that's all. Then in B we have to calculate the predicted population at t5 for each model. So all we need to do is just to substitute 5 as t. So these are our answers. And C. Which model would you recommend for long-term prediction? Explain. So as you can observe from your GDC, from both functions, exponential and logarithmic, you can observe that there are so Pearson correlation coefficient is very similar. So in this case we will use residuals, The difference between the actual value and predicted value. So we have only 4 numbers as days, so we will substitute all of them to both functions, and these are our actual answers. When we substitute t1, we will have probably a different value than 5. So the difference between the actual value and predicted value will be our residual. So firstly, let's substitute all values of t to both functions. So these are our answers after substituting t1, 2, 3, 4 to both models. Now we have to find the difference between actual value, so between our p5, 9.3, 14.1 and 18.2, and our values that we found after substituting t, and of course we are applying this to both models. So these are our answers, the differences between actual and predicted value, and now we have to raise to the second power every difference and then add them, but firstly for the first function and secondly for the second function. So these are our answers after calculating residuals. So we can observe that the first model, so our exponential model, has a much smaller value, so it fits better. So we're choosing exponential model. And D, discuss the limitations of using logarithmic models for population growth. So we can simply say it from our everyday life that, and of course from knowing how logarithmic function looks like. So basically logarithmic growth it increases very slowly. So basically for large t, it can severely unpredict populations that actually grow at compounding rates. And our final answer can look like this. And it was the last problem from this nonlinear modeling topic, as well as from the whole chapter functions. So stay tuned for the next chapter. And if you found this video helpful and useful, you can leave thumbs up, subscribe to my channel, and in case of any questions, you can write them down in the comments down below or via my mail that is, as always, in the description of the video. Bye!